Okay, I think it should be fine. So we're gonna do, yeah, my lecture is gonna be about angle chasing. So there isn't really that much theory behind angle chasing, but there's a few important things to remember, which are, first of all, cyclic quadrilaterals are important. So if we have a quadrilateral, we're just going to prove some basic properties about these angles and angles in circles in general. So first of all, like this might be, sorry, pretty basic geometry stuff, but yeah, I think it's important to see where, why can't I draw? To see where these come from. So first of all, let's say we have a circle, right? So let's say we have an angle here and an angle, whoops, and an angle. Let's say this is the center. We have an angle here and we have an angle here. So first of all, this angle is going to be double of this angle. And the reason for that is we can draw in this diameter. And so then what happens is if this angle is x and this angle is x, then this angle is 2x. If this angle is y and this angle is y, then this angle, we can show that it's 2y. So that way, we can see that this angle, which is 2x plus 2y, is double of this angle, which is x plus y. And as a result of this, we can show that in a cyclic quadrilateral, first of all, the opposite angles, these add up to 180 degrees. And also that if we take this angle and this angle, they're going to be equal. So these facts come up a lot when we do problems that involve angle chasing. And again, there's really not a lot of theory behind basic angle chasing. Like pretty basic geometry will be able to get you through most stuff that appears on AMCs. So one example of a fairly elementary angle chasing problem is, let's say we have a triangle. Actually, let's not draw that. Say we have a triangle and its circumcircle. And we'll say that this is its circumcenter. A, B, and C. And we're going to draw a circle passing through A and O. No, sorry. We're going to draw the line OB and intersect it with AC at P. And then we're going to take the circumcircle of AOP. So that's not a very good circle. How am I going to do this? You know what? Let's see. That's like pretty close to a right angle, right? So if you just kind of, there we go, close enough. Oh, I forgot to mention, first of all, like you probably know this, but every triangle has a circumscribed circle. Okay, that was also a terrible circle. But the reason is that we can take the, so it's important to know why this is true. So we can take the intersections of these perpendicular bisectors, right? And so since this is a perpendicular bisector, then this is equal to this. And since this is a perpendicular bisector, then this and this are equal. So it turns out that this point is equidistant from all three of the vertices of the triangle. So that means that it's the center of a circle passing through all three triangles. Yeah, well, I don't have a pen, unfortunately. So I'm gonna try my best. Yeah. So going back to the original problem, now that we've established that circumcircles exist, which is pretty important. No, I'm not using a stylus. It's not a great situation. But don't worry. Okay, so going back to the problem we were looking at earlier, let's see. No, you know what? I can't do this. That's better. Okay. So we have a circle, and then we have a triangle ABC. This is the problem we were just doing, and we're going back to it now. Let's have O be the circumcenter, right? And we have a point P here, which is the intersection of OB and AC. There's a circle tool. Yeah, maybe. I don't know. I can't figure this out. Okay, so then we're going to take the circumcircle of AOP. Where is this? Okay, there we go. That's better. And let's say that arc OP has measure 40 degrees. And we also know that AP equals OB. Then we want to find the measure of angle OBC. And oh, there is a circle tool. Oh, thank you. I should try that. But yeah, and we want to find the measure of angle OBC. So how are we going to do this? Well, we might go about doing this by first saying that we already established that if we have a, whoops, now it's stuck on drawing lines. Okay, this isn't good either. I don't actually, sorry about this. Oh, okay, that should work now. So earlier we established that, so we know that the measure of the arc is equal to this angle here. So earlier we established that this angle is double of this angle, right? So if the measure of arc OP is 40 degrees, then that means that the measure of angle OAP is half of that, which is 20 degrees. That's not the degree symbol. Okay, so this is 20 degrees. And we also know that AP equals OB. So what can we say from that? If AP equals OB, we also know that OB equals OA, since O is a circumcenter. So this is isosceles, that's fun. And we also know that OB is equal to OC, since this is a circumcenter, and we know that circumcenters exist. So now what are we gonna do? We can actually just, so first we know that this is isosceles, right? So angles AOP and APO are equal, so they're both 80 degrees. So these angles are both 80 degrees. So that means that angle OPC is consequently 100 degrees. That's this angle right here. And we also know that AO equals OC. So this is 20 degrees. This is 20 degrees. And as a result, since this is 100 degrees and this is 20 degrees, then angle POC is equal to 60 degrees, because the angles have to sum up to 180 degrees. So that means angle BOC, since this is 60, then angle BOC is equal to 120. And finally, since this triangle is isosceles, we have that angle OBC has to be 30 degrees. So that was a fairly elementary example, but there's more complex problems using what some basic things that we know about just circles and angles. So this problem is, this might be giving it away a little, but this problem is an example of how we can use cyclic quadrilaterals when angle chasing. So we have a triangle ABD, and we have an angle, so let's see, that is C, that is F, that is E. So, and we know that, let's see. We know that, first of all, angle ABF is equal to 80 degrees. We know that angle, let's see. We know that angle BFC equals angle BAC, which equals 40 degrees. So this is 80 BFC and BAC are both 40. So this is also 40 degrees. And we know that angle CBE So twice of angle CBE equals twice of angle FBE equals angle FEB. So we want to find the angle ADB. What does this equal? And the way we do this is, first of all, from this last condition, 2 times CBE equals 2 times FBE equals angle FEB. We can label this X. So this angle is also X. And consequently, this angle is 2X. And so now what can we do? So since this angle is X and this angle is 2X, then we see that angle DEB equals 180 minus 2X. And consequently, angle EDB equals X. Okay, so this is X. So as a result, this one is isosceles. And we also know what? Well, since this angle is 40 and this angle is 40, right, then quadrilateral AFCB is cyclic. So since it's cyclic, we can say that this angle is equal to angle FBT, which is equal to 2X. So as a result, the sum of the angles in the entire triangle ABD must equal 180. So we know this angle is 2X plus 40 plus, we know this angle is 2X plus 80 plus this angle, which is X, equals 180. So as a result, we can find that X is 12 degrees. And finally, we're going to go over one more problem, which this one is an AMC problem, but like it still really doesn't require much more than like the basic angle chasing principles that we've gone over. So we have a triangle. That's not a good diagram. We have a triangle. A, B, C. No, wait. A, B, C, and we have the circumcenter O. So, and we have the centroid, which, as you know, is the what's a good place to put the centroid? This is the centroid, which is the intersection of the 3 medians. I think Aaron might have mentioned this earlier, or I don't know, maybe he just talked about medians. And we also have the tangent at the circle, the tangent to the circle at A. And let's see. Oh, this is not, sorry, I drew this poorly again. But and we have the circumcenter O and the centroid G. And let's see, we have, what else do we have? We have the tangent to the circle at A and the line CO. These intersect each other at X. And XG meets the circle at Y. And we also have that the ratio of angle XOY to angle what? To angle B to angle C equals 17 to 13 to 2. And so we want to find, so let's see. So we're trying to find angle A. So the way we do this one is we take, basically we try to induce cyclic quadrilaterals into this diagram. Let me try to draw a few of these things better. Okay. Oh. Okay. And so now the way we do this is, since AG is a median, we can extend AG and it'll intersect BC at the midpoint of BC. And similarly, we can drop the altitude from O down to BC. And so that's going to be a right angle. And oh wait, no, I'm sorry. I'm sorry, wait. I misremember the problem statement. We actually have that. What we actually have is that we have O and we have the centroid G. And so we have, this is perpendicular. We have a line through G that is perpendicular to OG. And it intersects BC at Y. And we also have the tangent to the circle at A, and that intersects this line at X. So we have the same ratio of angles from earlier, XOY to angle B to angle C equals 17 to 13 to 2, and we want to find what angle A is. And the way we do this is, again, we can extend AG so it meets BC at the midpoint. So we can draw this perpendicular. And similarly, we can draw AO. So this is perpendicular. So then we can see that since OGY is a right angle and we'll call this M, OMY is a right angle, then OGMY is cyclic. And similarly, since this is a right angle and this right angle, OGXA is cyclic. So that means that this angle is equal to this. So that means that angle XYO is equal to angle AMO, and angle OXG is equal to angle OAG. And now what we can do from here is we can try to find, so that means that we know XOY equals 180 minus the sum of these angles, which is equal to 180 minus the sum of these angles, which is equal to angle AOM. And we'll show that this is equal to 2C plus A. And we can do this by drawing in line OB. So we can show that angle AOB equals 2C. And angle BOM is equal to half of angle BOC, which is equal to 2A. So angle BOM is just A. And so this is equal to C plus A, which is equal to 180 minus B. But now we're given the ratio between XOY, B, and C, right? So we can say that XOY is 17x. So then similarly, B is 13x and C is 2x. So equals 2x plus 180 minus 13x. And then solving this, we get that wait. Oh yeah, from this we get that 180 is equal to 28x. So then we can just solve for x. And once we know x, then we know that B and C are, B is 13x and C equals 2x. And so then we can find B plus C, and then we can find A equals 180 minus B plus C equals 585 over 7. Since from here we can solve for x, and then we can find B and C, which are 13x and 2x. Yeah, sorry for running over time, but the problem I'm going to leave you off with is something that I wrote a while ago. So let's say that we have triangle A, we have right triangle ABC. And AB equals 2, and we have a point D here such that AD is equal to 4. And then we take the circumcircle of BCD. Whoops. And then we draw in this diameter. So DE. And we know AE equals 10. AD equals 4. And AB equals 2. So the problem is to find the length of AC. Yeah, that's the problem that we're gonna leave off with, and it ends up involving angle chasing. So yeah, sorry for going over. If you have any questions, feel free to ask me. But yeah, otherwise we're done. Pythagorean theorem. Pythagorean theorem. I mean, it definitely involves the Pythagorean theorem.
I mean, like, you can't like make an entire like lecture out of the Pythagorean theorem, but like,
That's true. There's a lot of
like you have to know where it appears. Oh, I can use it to like find another length. Okay.
Yeah, the Pythagorean theorem does appear a lot in problems, as one would expect. Yeah, any questions? Otherwise, we're done about problems we went over, or just like geometry in general.